Anyway, thank you very much. All right. Okay. So that's for the second combination. Now for the third and fourth combination, these two combinations, in these two cases, look at the condition. What is the condition? The condition is that if P is true, then Q has to be true. If P is true, however, if P is true, then Q has to be true. If P is true, okay? If P is true. What happens when P is false? The condition doesn't say anything about that. If P is true, then Q has to be true. But if P is not true, then it doesn't matter what Q is. We don't even have to look at Q. As you can see in the third and fourth cases, P is false, which means the condition is not violated because P is not true in this case. The condition is that if P is true, then Q has to be true. All right. So since P is false, the condition is satisfied by default, so the output is true. Okay. So this is what we saw at the end of last session. Any questions regarding implications? Anybody has any confusion regarding implication? Please ask now because we will build on this. Does everybody understand how an implication works, the conditional statement?
Yes.
Yes, ma'am.
Okay.
Yes,
All right
ma'am.
then. All right. In that case, we can move into the biconditional statement. Okay. Oh, before that, sorry, I forgot. Before that, the converse of P implies Q. We use the term converse to represent the case of an implication where the position of the variable is switched. All right. So the converse of P implies Q is Q implies P, and these two are not equal to each other. All right. P implies Q is not equal to Q implies P. If you were to construct the truth table for Q implies P, you will see that it would have a different output compared to P implies Q for the same input combinations. All right. So basically, if you switch the positions of this variable, the truth value also changes. Okay. So these two are not equal to each other. And it makes sense. It only makes sense that these two would not be equal to each other, right? Because for this one, we have the condition if P, then Q. And this one, if Q, then P. The hypothesis has changed. This time, if Q is true, then P has to be true. The hypothesis and the conclusion both has changed. So of course, they're not going to be equal. Can anybody tell me, just by looking at the truth table of P implies Q, can anybody tell me why this will not be equal to Q implies P?
The third one will be
The
false.
third combination should be false.
Is that the only one?
The second one
And
will
the
be
second
true.
one will be true.
Exactly.
The
Very
second
good.
one would be true.
Very good. If you look at the truth table for P implies Q and compare it with what you understand by Q implies P, for the second case in P implies Q, the output is false. However, for Q implies P, for the same input combination for Q implies P, look at it. Q is false, right? So for Q implies P, if Q is true, then P has to be true. If Q is true. But in the second combination, Q is false. So by default, we can say that this does not violate the conditional statement Q implies P. So the output would be true for the same combination that you have in the second case. Okay. So just by looking at that, just by looking at the truth values, you can tell that P implies Q will not be equal to Q implies P. Okay. Any questions?
No.
Okay. All right then. Let's move on to a biconditional statement then. Okay. Let's look at the statement S first. The statement S says that it is raining if and only if it is wet outside. See, the condition has been rephrased or changed. The statement has been changed a little bit. If and only if. This if and only if is doubly binding. All right. As you see from the symbol here, the symbol that we use for a biconditional, the condition goes both ways. In case of an implication, in case of a normal implication, for this one, for example, the condition is if P is true, then Q has to be true. That's for P implies Q. And for Q implies P, if Q is true, then P has to be true. But each of these individually just have one condition. In case of a biconditional, however, it's doubly binding, right? So in order for this biconditional statement to be true, you have to satisfy both the conditional statements P implies Q and Q implies P. That is the difference between a biconditional statement and your simple implication or your simple conditional statement or unidirectional conditional statement. In case of a biconditional statement, you have to satisfy both the condition. For example, for this one, just for this statement, S, for S, represented by this biconditional statement. P if and only if Q, for this one, you have to satisfy not just this one, not just P implies Q, but also Q and Q implies P. So in case of a biconditional, both of these conditions have to be satisfied because it's doubly binding. P is true if and only if Q is true. And Q is true if and only if P is true. It goes both ways, okay? All right. So let's look at the truth table for S. S is represented by this statement here using this symbol for biconditional statement, as you can see. So let's just first look at the truth table for S. Okay. So the first combination where P is true and Q is true. The truth value of the biconditional statement is true here. And that makes sense because both of them are true. Obviously, it's going to be true. P is true if and only if Q is true. Both of them are true. So the output will be true. Or in other words, what did we talk about right at the start of discussing biconditional statement? When you have a biconditional statement, you have to satisfy the conditional statement in both directions. Okay, so you have to satisfy the condition P implies Q and also the statement Q implies P. So this case, the first case, satisfies the condition P implies Q. Yes, it does. It also satisfies the condition Q implies P. So that's why, since it satisfies both conditions, the output is true. Everybody clear with me so far? Is this clear to everybody so
Yes,
far?
ma'am.
Yes, ma'am.
Okay.
Yeah.
So the first case satisfies both the condition P implies Q and Q implies P. So the output is true. Let's look at the second case. Okay. For the second case, P implies Q. What is, we have to satisfy the condition P implies Q and Q implies P again, right? So let's look at the first condition. The first condition is what? P implies Q. For P implies Q, for that condition to be satisfied, what does P imply Q mean? P imply Q, what does it mean, guys? P implies Q?
If P is true, then
Q has to be true.
If P is true, then Q has to be true. Is P true in the second case? Is P true in
No.
the second case? Is
No.
P true in the second case?
Yes.
Yes.
Yes, it's true. The condition is that if P is true, then Q
Q
has to be true. Is Q true in the second case?
No.
So the first condition is not satisfied, all right?
Yes.
So we don't actually have to check Q implies P at all anymore because both conditions have to be satisfied, right? Both of them. If one of them is not satisfied, by default, we can say that this biconditional statement has been violated. So the output will be false. Let's look at the third case. The third case, for the third case, again, we'll look at the first condition. What was the first condition? P implies Q. For P implies Q, we have if P is true, then Q has to be true. This condition has to be satisfied. Now, if P is true, then Q has to be true. Okay, if P is true. Here, for the third case, as you can see, P is false. What is the condition again? If P is true, then Q has to be true. If P is true. So remember, from the previous case, P is false. So the first condition, if P is true, then Q has to be true. Guys, is that violated? The first condition, I'm just talking about the first condition. If P, then
Yes, miss, it's violated.
it's violated.
It's
No,
not
P
miss.
implies
violated.
Q.
It's
I'm
not.
just talking about P implies Q. Just,
It's not
But
violated.
Q is true.
Oh,
No,
miss,
ma'am,
like,
not
not
violated.
violated.
yeah, exactly.
It is, yes, miss. It's not
For the
violated. Sorry,
first
miss.
condition, just the first condition, the first condition that we have to satisfy, P implies Q, that hasn't been violated yet. Because the first condition, P implies Q, is the condition that if P is true, then Q has to be true. If P is true. For the third case, P is not true. So the hypothesis itself does not hold. So the condition, by default, there is no condition to be fulfilled since P is false. See, if P is true, then Q has to be true. If P is true. That is the condition. If P is true, then Q has to be true. But P is not true. The condition doesn't say anything about the case when P is false. So the condition by default is not violated. Okay. However, is that going to be enough for a biconditional statement? No.
No.
There are two conditions that have to be satisfied. Now we have two conditions. This is, you have to remember that this is a biconditional statement. So you have to satisfy both the condition P implies Q and Q implies P. So far we have seen that the conditional statement P implies Q is not violated. Okay. Now, what about Q implies P? We have to make sure that that condition is satisfied as well, that that condition holds as well, right? It's a biconditional. We have to look at both direction. P implies Q holds for the third case, fine. But does Q implies P hold? Does it?
No, it doesn't, because
It
P
does
is
not.
false.
Yes, because Q implies P means that if Q is true, then P must be true. Q is in fact true here. However, P is not true. So the second condition is not satisfied. The second condition has been violated. In order for the biconditional to be true, both conditions have to be satisfied. Both conditions have not been satisfied. The first one has been satisfied, but not the second one. So the output ultimately is false. Okay. Any questions so far?
No, miss.
Okay. Let's look at the last case then. P is false and Q is false. And now let's look at the conditional statements. This is a biconditional. Doubly binding goes both ways. So you have to satisfy both the condition P implies Q and Q implies P. For P implies Q, the condition is what? If P is true, then Q has to be true. If P is true. Is P true here? No. P is false. Since P is false, by default, the hypothesis is not there at all. So the conditional statement, there is no conditional statement to be broken at all, actually, because the condition starts with if P is true. P is false. So what is the condition? If P is true, then Q has to be true. If P is true, only then Q has to be true. But P is not true. So we are not worried about Q. All right. So by default, the first conditional statement has been satisfied. It is not violated. Let's look at the second conditional statement. Q implies P. If Q is true, then P has to be true. Is that one going to be violated, guys? The
No.
second one?
No.
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 Why is that?
Because by default, it's also true.
Yeah. Why? Because Q is false, right? Q implies P. If Q, then P. If Q, then P. Q is false. So by default, Q implies P is true. So both P implies Q is true and Q implies P is true. Since both conditions have been satisfied, what happens to the biconditional statement? It is true. Okay. So for the last case, false, false, the biconditional statement is true because both conditions have been satisfied since both of them are false. Everybody with me so far? Does the truth table so far, does it make sense logically?
Yes, ma'am.
No question. Okay. If that's the case, do you notice something that this biconditional statement can be used as an equality check for the input variables? Understand what I'm saying here. So the biconditional statement, based on the truth value of the biconditional statement, we can tell whether the input variables are equal to each other or not. Why is that? Look at the cases when the biconditional statement is true. The cases when the biconditional statement is true. What's going on with the input variables?
The truth values are actually
Yes, they have to be, both of them have to be either true or false.
That is, both of them have the same truth values,
Yes, miss.
right? When both of them have the same truth values, the output is true. So we can say that the output is true whenever the input variables are equal to each other. When are they going to be equal to each other? When they have the same truth values. So there is a relation between these things, all right? So there will be many, many relations like this. So this is what you have to do. This whole entire course is about logic and counting and critical thinking, right? So the more associations you find, the more relations you find between different ideas, the more developed your idea, your concept of discrete mathematics is going to be, and it's going to be that much easier for you to apply these concepts later on in other advanced courses or as a computer science engineer at any point of your career. All right. So try to notice this sorts of relation whenever, because there will be many relations like this. Every single idea can be represented in terms of another idea. All right. So for example, the idea of equality, the input variables being equal to each other or not, that is directly related with the truth value of the biconditional statement. Okay. So you see there is a direct relation here. Both if the input variables are equal to each other, we see that the biconditional statement has a truth value of true. Okay. So whenever the biconditional statement is true, we can say that the input variables are equal to each other. Or in other words, if they're equal to each other, we can say that the biconditional statement is going to be true, right? And if the biconditional statement is false, then it means that the input variables are different. They're not same. Now, in the previous case, for a conditional statement, P implies Q is not equal to Q implies P. That bit is clear to everybody, right? We cleared that out. Now, what happens when we switch the position of the variables for a biconditional statement? For example, the statement T. The statement T says that, claims that it is wet outside if and only if it is raining. What are the situations when this statement will be true? What are the scenarios when this statement will be true? It is wet outside if and only if it is raining. That is Q and P, the biconditional between these two with the positions reversed. It is actually the same thing as S. It will have the same truth value as S. That is, in case of a biconditional, even if you switch the positions of the variables, they will still have the same truth value. And it makes sense, right? Because in case of the first one, in case of S, P if and only if Q, you had to satisfy both the condition P implies Q and Q implies P. In case of the second statement, T, Q if and only if P. But does it really change anything? You still have to satisfy the same two conditions, all right? Q and P. So you still have to satisfy Q implies P and P implies Q. Both have to be satisfied. So nothing changes. So in case of biconditional, even if you switch the positions of the variables, it still means the same thing because this is doubly binding. Both conditions have to be satisfied either way. So it's the same thing. Okay. Any questions so far?
No, miss.
Okay.
No, miss.
So there was a student from the last session who asked, what will happen if we change these statements? That is, instead of say using the statement "it is raining," we say that P represents some other statement. Let's say it represents "it's sunny," or whatever. Let's say it represents that the statement "I am bored." Okay. Maybe one of you are bored, and it represents that statement. So she asked me what happens if these statements are changed. Let's say I'm going to represent it with "I am bored." I shouldn't actually use this statement. Okay, I'll use that as an example as well. What if we do this? All right. It is fine. The truth table will still remain the same for any statement you use here, as long as the statement is a proposition. "I am bored" is not actually the correct way to write a proposition. "I am bored" would not be actually a proposition. It talks about the current state of a specific person or whatever. We could say something like, "This is boring." Okay. Again, representing the mental state of some of you, I'm sure. "This is boring." So yeah, we can do something like that. What if we change the statement like that? Will it affect the truth table? Will it affect how the biconditional statement or the conditional statement, whatever, how the truth table behaves, how the truth values? Will it affect how what we get for the truth values for the given input combinations? No, it will not. You can use any statement in the world here as long as it's a proposition. It will not affect we use the statements here just to explain to you what happens when we use propositions here, but whichever statement you use, it doesn't matter. In fact, if you use contradictory statements, for that matter, if you use something like this, even this, it doesn't matter. It will make no difference in the entire world, absolutely no difference. Right? It doesn't even have to make sense. See, this is boring if and only if it is if this is interesting. Right? It doesn't have to make sense at all. It doesn't have to make sense. You can write whatever you want here. As long as it's a proposition, you're fine. So you see, it doesn't even have to make sense, but still the truth table remains the same. Remember, in these sessions, we have this little world here where we leave all the ideas of the practical world outside, right? Here, we strictly go by what we know in terms of propositional logic, okay? So whatever statement you use, it does not matter. All we care about is the truth values that we know of, okay? So this truth table would not be affected, whatever statement you use. Any questions? Anybody has any questions?
No, ma'am.
Okay. In that case, let's move on to the next concept, exclusive OR. Okay. So this is another operation outside of your basic operators, not and and or. So we saw the basic logical operators, not and and or. So an exclusive or, this is an extension of the or operation, or a restriction, or a further restriction on the or operation. So in case of the or operator, when is the or operator, when will the or operator have an output of true? Guys, when will the or operator have a truth value of true?
One input is true.
If either or all of them are true.
Exactly.
If at
And only
As
either one
long
of
as-
them is true.
As long as, not only, as long as at least one of them is true, the truth value of or is true, right? As long as at least one of them. So even when both of the input variables or all of the input variables are true, the truth value of or is going to be true, because the condition is that as long as at least one of them is true, as long as at least one, even if more than one is true, the output is going to be true. It will be false only when all of the input variables are false. So as long as at least one is true, the output will be true. XOR just puts another restriction on that. In case of XOR, the truth value, XOR is the short version, first of all. XOR is the short version of the term exclusive OR, right? So the truth value of the logical operator exclusive OR or XOR will be true when either only P is true or only Q is true in this case, right? That is when one of the input variables, and exclusively one of the input variables is true, all right? Exclusively one of the input variables is true. That is, one of the input variables has to be true, and while one of them is true, the other ones cannot be true, exclusively true, all right? So that is why you see that the first combination where P and Q, both of them are true, the truth value of P XOR Q is false, okay? This is the symbol that we use for XOR, and P XOR Q will have a false truth value when the input, both of the input variables are true, because they have to be true exclusively. If P is true, only P can be true, no other variable can be true. And if Q is true, only Q can be true, no other variable can be true, all right? So exclusively, they have to be true. So any questions?
Yes, miss. If will XOR be false when all of the propositions are true, or like more than one? Like in case of like 3 propositions.
In case of 3 propositions, it's the same thing, exclusive OR, right?
Yes.
So when one of them is true, only one of them can be true, exclusively true, all right? So exclusive OR. So yeah, at least one has to be true in order for the output to be true. But when one of the input variables is true, all the others cannot be true, or all the others has to be false, all right? So exclusively it has to be true, okay? Make
Okay.
sense? Okay. All right. So anybody else has any question? Does
Miss, can
everybody
you
understand
explain
this
the
truth
statement?
table here? Come again? So
Can you
this,
explain the statement that P XOR Q, this one, like
the
not
rest
Q?
of it is okay. Are you talking about this
Yes,
expression?
yes,
Yeah,
this
this one.
one.
Yeah, I'm gonna get there. I haven't talked about. I haven't touched upon that yet. But I'm talking about the truth table, just the truth table. Is this clear to everybody?
Yes,
Is
miss.
everybody clear with the definition of P XOR Q and what's going on here? The truth table of P XOR Q.
Yes, miss.
Yes, miss.
Okay. The purpose of this slide is not actually to tell you, impart knowledge upon you about an XOR gate. No, it's not. The purpose of this slide is actually this expression here. This is my main purpose, because we've talked to you about the basic logic operators, right? Logical operators, the not operator, and operator, and the or operator, right? We've talked about these things. Apart from this, there are other operations or other operators as well. Like you see the one here, XOR, there's XNOR. There are other operators like that as well. We're not going to touch upon all of those operators. If any of those operators come up in the exam, you can be sure that since they haven't been covered in the session, they will be explained or they will be defined in the question itself, all right? If they haven't been discussed in the session. The reason I'm mentioning exclusive OR here, the main purpose is this part here, okay? To show you that any expression or any statement in the entire world can actually be broken down by using some techniques, can be broken down into a statement combining just the basic operators, all right? You can represent any expression or any statement in the entire world to represent them using just the basic operators, as you see on the right hand side, with the expression on the right hand side. How do we do that? Now, how do we do that? I'll get to the why it works later on. First, I'll get to how we do that. What we do is one of the techniques, the one that I will show to you, is that you look at the output truth values and the cases or the input combinations which give you a truth value of true. You focus on them. Okay. In this entire truth table, which combinations give us a truth value of true?
The second and third.
Yes. So we will focus on these ones. All right. So we will focus on these two combinations or these two cases. Okay. So for the second one, for the second case, or you can say the first true case, for that one, we will look at the input variables, the values of the input variables first. So the value of the input variable P for this one is true, and for Q it's false. Now, when the value of the variable is true, we represent it in its normal form. When it's false, we represent it in its negated form. So P, for this second combination where the output is true, P is true, so we will represent it in its normal form, just P. For Q, it's false, so we will represent it in its negated form, that is not Q. Okay, so we represent it using P, and for this one, not Q. And how do we combine them? We combine them using an AND operator. So this expression that you see on the far right, P and not Q, this is the expression that represents the second scenario. Okay, we took a case where the output is true and represented that using an expression which only involves the basic operators. How did we do that? If there is a variable which has the truth value of true, we represent it in its normal form, as you see P here. If a variable has the truth value of false, then we represent it in its negated form, as you can see, not Q here, and combine those two using the AND operator. So P and not Q. This expression on the far right represents the second scenario here, right? The second case, where we get true for the input combinations of P is equal to true and Q is equal to false. Everybody with me so far? Everybody understands?
Miss, I have a question.
Yes.
Miss, last class you said like we don't even know if P is actually true or false.
Yes,
So
we don't
how
know.
can we, use Q as negated value of Q?
No, we are not saying that Q is always going to be false. We are not saying anything like that.
Okay.
This, I'm going to get to that. I hope it'll be clear just in a while. This is just an expression which represents this specific scenario, all right? We are not saying that Q will always be false. This expression, this specific expression represents this case, this second case that we have here. Represents only this second case, but we are not at all for once claiming that Q will always be false, okay? I'll just tell you now. So, but before we get to that, is it clear to you that this second scenario, the second case, can in fact be represented using this expression in this way?
Yes.
How we do this, like why it works, I'll get to that in a bit. But how we do it, is that clear to you? How it's done?
Yes, miss.
Yes.
Okay. Now, to the question, why does it work? Why is it that I am taking P in its normal form because it's true, Q in its negative form because it's false, and why am I using an AND operator? Why am I doing these things, and why does it work? Because, think about it. We have to represent this specific scenario using this expression, right? So you will see that this expression will be true only and only for these input combinations. This expression, the one on the far right, will be true only for this input combination. For all the other input combination, this expression, this one on the right-hand side, on the far right, will not be true. P and not Q will not be true for any other combination other than the second one. All right, you will see that. Okay, here we're using the AND operator, right? Since we're using the AND operator, and in order for the output or the truth value of the AND operator to be true, what is the condition, guys?
Both propositions need to be true.
Both have to be true, right? Both have to be true. Both P and not Q has to be true. Now, let's look at the truth value of P. The truth value of P, what is it? In the second scenario, in the second case, true.
True.
Okay? But that is not enough. That is not going to be enough because this is an AND operation. We also have to look at not Q. Now we have not Q here. In order for not Q to be true, Q has to be what, guys?
False.
False. Because if Q is false, only then not Q will be true. Let's see. Is Q false here in the second case? Yes, it's false here.
Yes.
So not Q is going to be true. So P is true, not Q is true. We have true and true. What is going to be the result for this AND operation?
False.
True.
What?
True.
Why false?
Because both of the truth value has to be true.
Yeah. P is true. Yes, good. And I think you're confused because Q is false here, right? But
Yeah.
you see, we used not Q here. If Q is false here we have in the expression not Q. Even though Q is false here, this one becomes what? Not Q. What happens to not Q? This is negation, right? What does negation do? If the thing that you're applying the negation of, if that thing is false, the negation will convert it into true. If that thing is true, then it will convert it into false. All right?
Yes, ma'am.
If that's not clear, then you have to go ahead and ask now, all right? Because this is something that you'll apply not only in this course, but in other courses, and you'll have other applications of this as well, okay? So the result of this AND operation between P and not Q is going to be true, in fact, because P is true and not Q, I'm talking about not Q. Not Q is also going to be true because in the second case, Q is false. And if you apply the negation on false, what happens to it? It becomes true. So true here and true here. So the result of P and not Q is going to be true. Anybody has any confusion with this? Everybody understands this?
Yes, ma'am.
Okay, all right. If this is clear to you, now you see that the second scenario is actually expressed by this expression. All right? The second scenario, when P is true and Q is false, the output is true. When P is true and Q is false, not Q becomes true. So the result is true. So this is depicted by the second scenario. All right? Second scenario and this one, they're equivalent to each other. Also, on top of that, this expression will be true only and only for the second case. If you apply the truth values of any of the other cases or the other combination, you will see that you will not get the truth value for this expression. This expression only represents the second scenario. All right. So that is why we are using this negation. All right. Because our goal here is to come up or create an expression using only and, or, and not. Create an expression which represents this second case. That is our goal. How do we do that? The second case, all right, we are taking only the cases which have output as true, right? The output is true. Only those cases where the output is true, only those cases we are taking. In the second scenario, the output is true. So we have to make sure that this expression evaluates to true for these combinations. So P is true, so it will be in its natural form. Fine. So when P is true, this is true. Okay. And then Q. Here we have false. So we will put a not Q here so that this becomes true here. And in between, we will put an and. Why is that? Because both of these conditions have to be satisfied. This is the combination, right? This is the combination where P has to be true and Q has to be false. This is the combination. That is why we are using an and. So this expression depicts the scenario we have in the second case and only that one. You will see that if you apply true, the first case here, P is true, fine. But is that going to be enough, guys, for the AND operation to be true?
No, ma'am.
No. So we look at the truth value of Q. For the first case, the truth value of Q is true. For the first case, Q has true truth value. What happens here? This is not Q. What will happen to not Q?
False.
False. So we have true and false. So P is true. So the result of this AND operation is going to be true, right?
False.
False, yeah. So the result is going to be false because even though P is true, not Q is false. Because you have true for Q here, not Q is the opposite of that. False, true, and false give you false. Similarly, for all the other scenarios, you will see that this does not give a truth value of true. This will give a truth value of true. This expression gives a truth value of true only for the second combination. All right. That is why we are using these specific operators. Not Q because Q is false, and the AND operator in between to make sure that this gives a truth value of true only for this combination, none of the others. That's why we have AND here. All right.
Ma'am, why row number
Yes.
1 is false? Can you explain that again? With
Row
this-
number 1 is false for this expression. This
Yes,
expression.
why? Yes, why?
Just apply the truth values. Think about it. You do it. You do it. You tell me. In this expression, apply the truth values that you have for P and Q. P is true here. Apply the true here. P is true. Fine. But we are trying to evaluate the truth value of this expression, P and not Q, right? So there's an AND operation. So only one side, that is only P being true, is not going to be enough. This side, not Q, has to be true as well, right? Do you understand that?
Yes, ma'am.
Okay. So in the first case, what is the truth value of Q?
Yes, true, ma'am.
True. What happens when you apply the negation on Q?
It becomes false,
Exactly. In the expression, what do we have? Do we have Q or not Q?
not true.
Not Q. So Q here was true and here it became false, right? So you have true for P and false for not Q. True and false. In case of an AND operation, for an AND operation to be true, both of the variables have to have the truth value of true. Do both of them have truth values? No. So that is why it's false for the first scenario.
Thank you.
Do the third scenario again, just to make things clear. For the third case, for example, what is the truth value of P for the third case, guys?
False.
False.
False. So here, for P, what will we have? False.
False.
Guys, do we even need to check the truth
No.
value of not Q?
Yes.
Yes, we do?
Yes,
No,
because
we
it's an
don't.
AND.
Okay,
If-
let's
if
go
it's
back to
an
the
AND,
definition of
we just
AND.
need to check one because all of it has to be true.
Okay, so yeah, so let's just go back to the definition of AND. What is the definition of AND? Think
Both
about
of
the
the-
truth table of AND. Yeah, go ahead.
When all of
All
the
of propositions need to be true.
All the propositions need to be true in order for the output to be true,
True.
right? So when you see that P is false, you already know that all of them are not true. If P is false, how can all of them be true, right? P is false. You already know that P is false. So you don't even have to check not Q. You know that this is going to be false, right? If P were true, then you'd have to check the second one because the condition is that all of them have to be true. If P is false, already know that all of them are not true. So the output is going to be false. Does it make sense now?
Yes.
Yes.
Okay. All right, sir. So see, for the third case as well, since P is false, this expression is false. And the fourth case as well, again, P is false. You don't have to even check, need to check not Q. P is false. So here you will get false, false, and whatever will give you false. So as you can see, this expression is true only and only for the second scenario, only and only for the second case. Okay. So that is why and how we represent a case where the output is true using an expression like this. Okay.
Miss.
So here
I have
we're not
one
necessarily saying that Q is always going to be false. We are just representing this specific case where Q is false. This specific case is represented by not Q, just to make sure that this expression depicts this scenario and that this expression is true only and only for this scenario. Okay. Okay.
Miss,
Was
can I
there a
ask a
question?
question?
Yes. Go ahead.
Miss, we can also find a true outcome with another expression using OR. Like for
Sir,
the second,
sorry, come again.
for the second combination, we can use OR operator and find a true value.
Yeah, there's another way to do that. Yeah, like if you use the OR operator,
Yes, Miss.
you're saying that, okay, if you do P or not Q, it will still come to be true, right?
Yes, Miss. Yes, Miss.
Yes. However, will you have the, is it going to be true only for the second case and not the others? Think about what you're saying here. You're saying in case of and, here, what if we use or, right? So
Yes,
if
miss.
you do that, then this expression becomes true for the second case, right? But it
Yes.
also becomes true for the first case, which we do not want. If this expression becomes true for the first case, then you're wrong there. We are trying to express P XOR Q using these expressions. For P XOR Q, the first expression, it's false, right?
Yes,
However, if you use OR here, this will give you true, right?
Okay, okay, yes.
Do you understand that now?
Yes, Miss.
Okay, so that is why we need to use an AND to make sure that this expression represents this case, yes, but exclusive only this case, all right? This expression should represent only this case, okay? Now we'll move on to the next case which has a truth value of true. Which one is that? The third combination. Now in the third combination, P has false. So how will we represent P, guys? In the normal form or the negated form?
Negative form.
Exactly. And for Q, the truth value is what? True. So what will we do?
Keep it as like, keep it as
Keep it in the normal form, all right?
Okay.
And then combine those two using an AND. So you have this expression, not P and Q, which represents the third scenario. And similarly, you will see that this expression is true when P is false and Q is true. If P is false, what happens to not P, guys? The third case, P is false, right? What will happen to not P? Now, what will be the value of not P?
Not
It
true.
will be
It became true.
Yes, exactly. But will that be enough to make the AND operation true? No. We also have to look at Q. Okay, now what is the truth value of Q
True.
for the third case? True. So both of them are true. We can say now, finally, it's safe to say that this operation, this expression will give us a truth value of true for this specific input combination, the third one, all right? And also, similarly, you will see that it will only give you true for this combination, none of the others. None of the other combination, for none of the other combination, we will get a true truth value, all right? For example, apply the second combination for this expression. P is true for the second case. What happens to not P, guys?
It becomes
False.
False.
It becomes false. This is an AND operation, not P. If this side is false, by default, the entire operation becomes false. Even if you look at Q, it's false, all right? So this operation evaluates, sorry, this expression evaluates to false for the second case. You will see That's what happens for the other combinations as well. So this expression will be true only and only for this combination, P and Q being false and true respectively. All right. So that's how, and that is why we can use this expression to represent this specific scenario. All right. Now that we have done that for each of these cases where the output is true, now we have an OR here. Why do we have an OR here? Because think about it. Both of these give a truth value of true. And in P XOR Q, you have two truths, right? So P XOR Q, in other words, you can explain it like if that P XOR Q will be true when either P and Q are true and false respectively, or when P and Q are false and true respectively. All right. If either one of these combinations are followed, or if either one of these conditions are followed, then P XOR Q is going to be true, right? So as long as either one of these expressions representing these two cases, as long as either one of these expressions is true, the output will be true. All right. So that's why we have an OR here. Okay. So the method is that you look at the truth table, you come up with, you identify all the cases where the output is true, and for each of the true cases, you look at the input combination, come up with these expressions, then you make the expression for each of the individual cases and then combine them with an OR. All right. That is how you represent, or you break down a certain statement into a statement that has only basic operators. All right. And why does this work? Because you have an OR here. You have an OR here. What does this represent? It represents the fact that as long as any one of these expressions is true, the output will be true. That is what we see here as well. As long as any one of these combinations are followed, the output is true. However, if you follow any one of the first combination or the fourth combination, the output will be false. You will see if you create the truth table for this expression, you will see that it is the exact truth table as this one. All right. You will see that for the first case and the fourth case, the output is
all
false.
the combinations.
Come again?
Means, do we have to write all the combinations, or we can write any of them?
All the combinations, all the true combinations.
Okay, miss.
Is your question whether you have to write down all the true combinations
Yes,
or
yes.
all combinations?
Yes, I got that.
Okay, all right. So you have to jot down all the true combination, and it makes sense, right? When, like, think about it. If you only represented P XOR Q with just this expression, if you left this one out, if you just said that P XOR Q is equal to not P and Q, then that would be wrong. Because what would that mean? By that you would be saying that the expression will be true only for not P and Q. That is, the expression will be true only for the third combination. However, the expression is true for both the third combination and the second combination. So you have to take in the expression for the second combination as well, right? Does it make sense now?
Yes, miss.
Okay.
Yes,
So you have to take in all of them, because if you leave out any one of them, what does that mean? See here, these two expressions represent which combinations? The second one and third one. Do you see any expression for the first one or the fourth one? No. Why? Because the first one and the fourth one have a truth value of false, and we are not concerned about that. Okay. So truth value of false, so they will not be counted in. Because they have a truth value of false, that's why we don't have them here. If you had them here, then it would be wrong. It would be incorrect. Because if you put an OR here and then wrote down the expression for this combination, it would mean that the output is true for this combination as well, which is not the case. So that is why what we do is we first look at only those combinations where the output is true, write down the expression in this manner for those combinations, and then combine the two expressions together with an OR in between. All right? That's what we do. And this expression, this entire expression together, means that the output will be true when either this one is true or this one is true. All right? And that is what we see here. The output is true either when this combination is true or this combination, either when this combination is followed or this combination is followed, not for anything else. Any questions?
Yes, miss.
Yeah.
Miss, for this XOR, do we have to like see the truth table, and from that we have to find the expression, or the expression will be given?
Does it matter? Shouldn't you be able to do both? If the truth table is given for XOR, let's say, you should be able to derive the expression from that.
Yes, miss.
Or if the expression, if the expression itself is given, then you can compute the truth value of this one, or create the truth table for this expression and see that P XOR Q's truth value is equal to this one.
Yes,
Do you
miss.
understand what I'm saying? Both ways can be done. If you have the truth table of P XOR Q and you're asked to derive an expression, that is, the expression is not given and you have to derive the expression, you can do that by looking at the truth table of P XOR Q. All right?
Yes, miss.
Actually, in fact, the P XOR Q truth table doesn't have to be given to you at all. If you know the definition of P XOR Q, you can construct the truth table of P XOR Q itself. In fact, in the question paper, you will see that none of the truth table of AND or NOT, none of them will be given to you. You know the definition, so you should be able to know what the truth table is going to look like. So once you create the truth table for P XOR Q, from that one, you can derive this expression. Or in other words, if this expression is given and you have to prove that these two are equal, you can create the truth table of this one, you can create the truth table of this one, and show that both of them have the same truth values for the same input combinations. All right?
Yes,
Any
miss.
other questions?
No, miss.
Okay. Why don't you guys try to do the same thing for some other expression? So this is a technique. There is another technique actually. One of you were talking about what would happen when this AND would be changed into OR. All right. So it wouldn't work for this specific technique. However, here we focused on the truth, is focused on the input combination where the truth value was true, right? There's another technique where we focus on the false truth values instead, only on the false truth values. For that one, the whole process is just completely reversed. That is where you apply the negation, you apply on the opposite one. Where you applied AND, you apply OR. Where you applied OR, you apply AND. We're not going to look at that. Where this technique, I think this technique will be enough for you guys at any situation. You can just look at the truth values and derive the expression. All right, so the other technique, I'm not going to go over that here. However, if any of you are curious and you want to find out about that, you can always send me an email and schedule a consultation session, and we can talk about that later. I'm not going to cover it here. This is going to be enough for you to break down any expression in the entire world and break it down to basic operators, all right, or derive an expression using a basic operator from any expression or any statement in the world. Okay, so let's just do that. Or this one. So let's say, for example, we had the implication, right? So for this implication, P implies Q. For this conditional statement, P implies Q as well, you can actually break it down into an expression involving only the basic operators. How do we do that? Again, the same process, the same method. We focus on the combinations which give us a truth value of true. All right. So the first one will be counted, the third one will be counted, and the fourth one will be counted. Clear so far, guys?
Yes, ma'am.
Yes, ma'am.
Okay. So what is the first thing that we do? For each of the input combinations which give us a truth value of true, we derive an expression for those combinations. So for example, for the first one, all right, we have an output of true. So we will look at the input combination of this one. What is the input combination? True, true. P is true, Q is true. So how will we represent this? Will they be in their normal form or negated form?
This normal form.
Normal form. Which one will be in the normal form?
This P has to be in the normal form.
Only P?
No, Miss Q also.
So both P and Q are going to be in the normal form, right? So you will have this expression first. Okay? So you will have, first of all, this P and Q. But is this enough, guys? Is this going to represent P implies Q?
No, Miss.
No, it's not going to do that. because this expression means that it's true only for this combination, none of the others. You have to incorporate the other combinations as well where the output was true. All right. So you have to do that for the third case and the fourth case as well, basically. So for the third case, for the third input combination, you guys should be able to tell me now what should be the expression for the third case. P is false, Q is true.
Miss not P and Q.
Exactly. Very good. So we will have not P and Q here. Okay. So we will have not P and Q. Right? And finally, for the last one, what will we get?
Not P and
not Q.
Exactly. So we will get not P and not Q. Right? Is this clear to everybody? These are the three expressions that we will get for the three combinations for which we have the truth value of true. So we have the expressions. How do we combine these expressions, guys, then?
With
Or. We use an or in the middle, right? We use an or in the middle. So you have or in the middle. Okay, that is how you do it. Clear, everybody? Any questions?
No, Miss.
Okay. Okay. Some terminologies that you need to familiarize yourself with. We've already talked about converse. You need to familiarize with yourself with these terms. Converse. The converse of an implication is the implication when you switch the position of the variables. All right. So for example, the converse of P implies Q would be Q implies P when you switch the position of the variable. And the converse of an implication is not going to be equal to the original implication itself. All right. The converse is not going to be equal to the implication. So that is, we've already seen this, right? We already know this. Just the thing that you have to remember is the terminology that we use in these cases. When you have P implies Q, if you switch the position of P and Q, we say that it's the converse of P implies Q. So Q implies Q is the converse of P implies Q, and P implies Q is the converse of Q implies P, and they are not equal to each other. Okay. Contrapositive. We use the term contrapositive when we apply the negation on the variables and then we switch the position of the variables. So if you have an implication P implies Q, you apply the negation operator on both P and Q and then switch the position. All right. So you have not Q implies not P. First we applied the negation and then we switch the positions and then we have not Q implies not P. Interestingly, the contrapositive of an implication is equal to the implication itself. All right. So P implies Q is actually going to be equal to not Q implies not P. That is, both of them are going to have the same truth values. All right. I'm not going to construct the truth table for not Q implies not P. I'll leave that for your homework. I've shown you enough examples of truth table. I assume you should be able to do this by now. So practice this, try this out at home. If you're not able to do this, if you're confused, you can always send me an email. You can always ask me questions in consultation sessions or in the next session or whatever, but try this out. You need to try this out to make sure that you're able to do this by this point. You should be able to do this by this point. Construct the truth table of not Q implies not P and see whether the truth values match up with the truth values for the implication P implies Q. You will see that they should match, okay? Because the rule is that the contrapositive of an implication will be equal to the implication itself. Okay. All right. Now, a compound proposition. What is a compound proposition? A compound proposition is a combination of propositional variables using logical operators. An expression which is formed using propositional variables, and the propositional variables are combined using logical operators. All right. You have actually already seen examples of compound proposition. Can somebody tell me where you might have seen examples?
XOR expressions.
Exactly. Very good. What is this? The one on the right hand side. What is this? This is a compound proposition. This is an expression where you have propositional variables combined using logical operators. This is a compound proposition. Okay. Any other examples that you might have? Any other example? What about this one?
Miss
What
P
is-
implies Q.
Sorry? Yeah, exactly.
Only P implies Q with the symbol imply. Is it a compound proposition?
This one. No,
Yes,
no, no.
Why
This
not?
is not a compound proposition because you have only one logical operator here, all right? You have only one logical operator which connects two variables, all right? A compound proposition is an expression where you combine multiple logical variables together with multiple logical operators. That's why the term compound. This is not compound. This is a proposition, yes, but this is not compound, all right?
Yes, ma'am. Buchi.
Okay. All right. Okay. No. All right. Sorry. Let me reverse that. What I said was actually, yeah. I got confused between compound and complex. You're right. P implies Q is also can be thought of as a compound proposition. What this is it's a compound proposition. Also, it's a simple proposition, but it's not a complex one. This is a complex one. This is not complex. We're not going to look into complex. I got confused there. I'm really sorry, guys. Yes, this can also be assumed to be a compound proposition. Any case, any situation where you have a logical operator involved, that can be the compound proposition. The term compound proposition can be used to represent that specific expression. All right. So P implies Q should be a compound proposition as well. Yes, this is a compound proposition. Sorry about that. All right. So any expression where you have any logical operators involved is a compound proposition. What this is not is a complex proposition. A complex proposition is this one. But we are not going to look into the difference between those in these sessions or in this course for that matter. That is not very important. It doesn't have too many applications either. The only term that you need to know is compound proposition. Any expression where you combine multiple propositional variables using logical operators is a compound proposition. All right.
Let's have a question.
Okay. Yeah.
Let's
Go
have a
ahead.
question. If P or Q, if the statement is like P or Q, it's not a compound proposition, right?
No, it's a compound proposition.
But we have only one logical operator. That's
Yeah,
like,
yeah. That is what that's my bad. Actually, that is what I wanted to clear up. No, it's a compound proposition. Whenever, so see, it is raining is a simple proposition. It is wet outside is a simple proposition. Whenever you bring in a logical operator, what happens? You are combining two propositions into one. So a compound proposition, all right?
okay, got it.
So when you have P or Q, for example, it is raining or it is wet outside, all right? So yeah, P or Q. It is raining or it is wet outside. It is raining is a simple proposition. It is wet outside is a simple proposition. But here, what are you doing? You're combining two propositions using a logical operator. So this becomes compound, right? Is that clear now?
And what if, like, for complex propositions, P or Q is not a complex proposition, right?
No, it wouldn't be complex. But you don't have to be worried about that. We are not going to distinguish between complex and compound. Like all complex propositions are also compound propositions, all right? So we're not going to distinguish between them. This is not an example of a complex proposition. P or Q is not a complex proposition, yes. But all complex propositions are also compound propositions. So we are not going to go into into that difference for this course, because that doesn't serve too many applications. So we're not going to bring in too many concepts. So you don't have to be worried about that. But to answer your question, yes, P or Q is not a complex proposition. However, you should bear in mind that this expression, for example, which is quite complex, is also a compound proposition. Any proposition where you bring in more than one propositions and combine them using a logical operator or multiple logical operators is a compound proposition. All right. Is that clear now?
Yes.
Ma'am, could you go to the conditional statement page?
Yeah, sure.
Yeah, here we represented P implies Q with R, right?
Yeah.
So when we draw the truth table, so can we write R instead of P implies Q?
Yes, you can.
Okay.
But it doesn't change the fact that R is still a compound proposition. Yeah?
Yes, ma'am.
Okay. So when we get to compound proposition, we also have to know about the order of precedence. That is, if you do have a compound proposition like this, we just did this, fine. But there is a combination of logical operators. You have not operator, you have and, you have or. Which one will you apply first? Which one later? Which one comes first? Which one comes after? How do we know that? There is an order of precedence. Also, there is parenthesis, right? So always, by default, parenthesis comes first. That is something that we know from BODMAS or PEMDAS, right? Parentheses always come first. So apart from parenthesis, for the basic operators, not and or, the precedence goes like not has the highest precedence. That is, for any compound proposition, after you apply the parenthesis, the first operation that you go for is the negation operation. Not comes first. And then you apply the operation of and then or, and then the implications. All right. So this is the order of precedence. Okay. So if you have something like this, not P and Q, what you do is you first apply the negation on the P propositional variable. All right. So this is equivalent to applying the negation operator first. So that's why you have the parenthesis here. And then the AND operator. In the question, you will not have it expressed in this format. All right. It will not be so clear. If you see something like this, not P and Q, you should know just by looking at this that, okay, first I have to apply the negation operator and then the rest of it. So this is not equivalent to this one. If you have something like this, because of the parenthesis, what do we do? Because of the parenthesis, we apply the AND operation first and then we apply the negation. However, if the parentheses weren't there, if it were in this form, then you apply the negation operator on P first, and then the result that you get from here, that one, you apply the AND operation between that one and Q. All right. Similarly, P or Q implies R. Here, which one will get the higher precedence? Or, as you see in the order of precedence, implication comes later. So for the OR operation, so for this one, even though there is no parenthesis, even though there is no parenthesis, the OR operation will take place first, and then you apply the implication. So this is equivalent to this. Even if you don't include the parentheses, you know that, okay, I have to apply the OR operation first and then the implication. Okay, there was a question, I think.
Yes, miss. This order of precedence is like number 1 first, then number 2. If can we use OR first and then AND?
Usually, if there's a combination of OR and AND, then parenthesis will be used. Parenthesis will be given, and from you as well. It is expected that if there is OR and AND, you will use parenthesis to show which one goes first and which one goes later. And if at any rate, for any given scenario, if there are no parentheses and there's a combination of and OR, we go by BODMAS or PEMDAS again and go with the multiplication operation first. That is, we go with the AND operation first, right?
Okay, miss.
Okay, but it is expected. Let's say, for example, you write down a logical expression, you derive something. If there's a combination of and OR, it is expected that you use parentheses to show which one comes first and which one comes later. If the parenthesis is not there, at any rate, we assume that and goes first, then OR. All right?
Yes, miss.
Okay, any other question? All right, then. So, finding the truth table from a compound proposition. How do we do that? So we have a compound proposition here. How do we compute the truth table of this compound proposition? First of all, how many propositional variables do we have in this proposition, guys?
Yes, 2.
2, P and Q, right? So the first thing we do is come up with all possible combinations of truth values of PQ. How many combinations will we get, guys?
4.
4. True, 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 false, false, true, false, false, right?
Yes.
So, and then for each of these combinations, what we do is we apply the values in this proposition and see what we get in the result. Let's do the first one. Then it will become clear. For the first one, P is true and Q is true. What will we do? We apply P true and Q true here in this proposition. And then we will see what we get in the result. Okay. So, order of precedence. Which one will come first? Parenthesis. So we will look at the parentheses first. So this one and this one. Okay, let's go from left to right. So this one. So in this parenthesis here, we have, within this, we have an or and a not, a negation and an or. Which operation will take place first? Or?
Not.
Not. Not is the operation that will take place first. We apply the negation operator first based on order of precedence. So first thing we will do is apply the negation operation on who? On Q. So we will compute not Q first. In the first case, what is the truth value of Q?
True.
What will happen to not Q?
False.
False. After you apply the negation, not Q will become false. So we have false on this side. So since we have false on this side, what will we do next? We will apply the OR operator. Okay. So we have false on this side. So what is the result going to be? False, right? For this OR operation?
No,
It's
Right?
gonna be true.
we need
True.
a true.
It's going to be true.
What? We have to
We
check
need-
what?
We have to check another, like the other proposition.
We have to check the value of P. Why? Because this is an OR operation. In case of an OR operation, what is the definition? As long as at least one is true, we will get true. Even though on this side, not Q is false, since this is an OR operation, we still have to check the truth value of P. What is the truth value of P?
True.
True.
So we have true or false. So what will be the truth value of this expression?
True.
Because this is an OR
True.
operator, since P is true, the expression becomes true. Okay, that bit is done. Next, we go move on to the next parenthesis. We move on to this parenthesis, all right? So here, inside this parenthesis, what do we have? Just a single operator, and, all right? So we need to check the values of P and Q. What is the truth value of P, guys? For the first case, true?
True.
So since P is true, by default, it makes the entire operation true, right?
Not really.
No.
No, it does
we need to
not.
consider
This
true.
is an AND operation, so we also need to check the truth value of Q. However, for the first case, the truth value of Q is also true. Since both P and Q are true, and this is an AND operation, we have true and true, so this expression will give us true. So on the left-hand side, this expression gave us true, remember? And for this one as well, we got true. So what do we have? True
True.
implies true. In case of an implication, what is the condition? If the
Yes,
left-hand side is true, then the right-hand side must be true as well, right? Now, if the left-hand side is true, the left-hand side is true, in fact. So the right-hand side has to be true. Is the right-hand side true, guys?
Yes.
Yes.
Yes, it's true.
Yes, yes.
So the condition is satisfied, right? The condition of the implication is satisfied. So we can say that the output of this entire expression will evaluate to true. All right. Does anybody has any question so far?
No, ma'am.
No.
No,
Okay,
ma'am.
good. All right. So you can do the same thing for all the other combinations. Okay. So same goes for the second, third, and fourth combination. You apply, let's say for the fourth combination, for example, you apply false, false on all of these values. P will be false, not Q will become true. P here will be false, this one will be false. You do that and then you compute the final result. All right.
Ma'am, in implication, the false is actually true. So
Sorry?
when we normally apply implication, when
Yeah.
P is false and Q is false, then the final product is basically true. But here it is false, so I'm kind of confused.
Yeah, I was actually waiting for that because that is a question that I got in the last session as well. So yeah, if any of you are confused, because if you remember for an implication, when for P implies Q, when both are false, the output is actually true. In fact, if P is false, by default, the output becomes true. However, you cannot apply that logic here. Why? Because here, think about it. The last scenario here, false, false. Are you applying the implication on just P and Q? Here,
No,
look
P
at the
and not
left-hand side
Q.
and the right-hand side. Do you have just P on the left-hand side and Q on the right-hand side?
No.
No, miss.
No. We have compound propositions on the left-hand side and compound proposition on the right-hand side. So first we need to calculate the value of the compound proposition on this side. Whatever we get here, based on that, we will compute the value of the implication, all right? Yes, for P implies Q, strictly for P implies Q, if both P and Q are false, the output is true. But here, it's not P implies Q. This is not, on the left-hand side of the implication, it's not P, on the right-hand side, it's not just simply Q, all right? So what you need to do here for false false is apply the false here in P and the false of Q here in not Q, which will give you true. And then, just like the first case, compute the value, all right? So this is something that I'm expecting you guys to do back home. I'm expecting you guys to apply these truth values to this entire expression and calculate each of those values and then see if this is the result that you get. This is the correct answer. See if this is the result that you get. You must do this to make sure that this is something that you can do by now. This is something you should be able to do by now, so do that. In case anybody out there is confused when applying these values directly here, just like we did now, if you're confused there, you can break it down, all right? Let me show you an example. We will do a long way down the road. For example, don't focus on the rest of the question. We will do that later on. Just look at this expression on the right-hand side. P or Q and P or R. This expression. We need to compute the truth values of this expression. So we have 3 variables here. So 8 combinations of truth values. And for each of those, what we did was we first calculated the truth value of P or Q, this one, and then the truth value of P or R. See, for P or Q, we have calculated the truth value. For P or R, we have calculated the truth value, and then performed the AND operation between these values in order to get the final result of the truth value of this entire expression on the right-hand side. So you can do something like this as well. All right. So introduce more columns in the truth table to make things clearer to you guys. All right. If any of you find it confusing or overwhelming, what you can do is here you can introduce other columns. For example, you can introduce a column dedicated for not Q, where you compute the result for not Q. Then another column where you compute the result for P or not Q. Then another column where you compute the result for P and Q. So each of them individually gets a column. And then finally, you compute the result of the implication. All right, you can do something like that as well if that helps you out. Break it down. Okay. However, if you're comfortable applying the truth values directly here, you can do that as well. Initially, many of the students find that applying the truth values individually makes things clearer for them, just like this one here. So in order to calculate the truth value of the expression on the right-hand side, which is P or Q and P or R, what did we do? We first calculated the truth value of P or Q, and then calculated the truth value of P or R, and then applied this AND operation on these truth values. All right. So this made things a little simpler. All right. So you can do that if to make things a bit simpler for you guys. And maybe after a lot of practice, you can directly calculate the truth values. All right. So this is something that I'm expecting you guys to do back home and check with this table. And if it matches, then good. You're in the right track. If it doesn't match, then you must have done something wrong. You can definitely send me your work and I can tell you what went wrong if you want my feedback. All right. And if you have any questions so far as well, you can send me an email regarding that. Okay. I'll stop the recording at this point. If you